And so now we'll look at calculating exact values for 45 degrees, 60 degrees and 30 degrees, and these can be done from what are called the special triangles. There are other ways to also remember these, and we'll have a look at a couple of different ways, but we're going to generate the exact values using the special triangles. So as I said, we'll be able to calculate exact values for sine, cos and tan of 45 degrees or pi on 4, sine, cos and tan of 60 degrees or pi on 3, and sine, cos and tan of 30 degrees or pi on 6. And all we need to recall these two triangles, and then it's just some simple Year 9 trigonometry, SOHCAHTOA sort of stuff. So the first of the special triangles is created by halving an equilateral triangle of side length 2. So we know an equilateral triangle has 3 equal angles of 60 degrees. So when we halve such a triangle, we end up with a right-angled triangle with angles of 60 degrees and 30 degrees. And since we've halved it down the middle, we now have, we still have a hypotenuse length of 2, we have a side length of 1, and using those two side lengths and the fact that the triangle is right angled, we can use Pythagoras' theorem to calculate that the third side is root 3. And it becomes quite easy to just remember that. You don't need to do it each time. The second of the special triangles is a right-angled isosceles triangle with equal sides of length 1. So being a right-angled isosceles triangle, clearly it has a right angle and the other two angles must be equal, so they are each 45 degrees. And the two equal side lengths are 1, and again Pythagoras' theorem can be used to calculate that the hypotenuse length in this triangle will be root 2. So now let's have a look at how this is going to work to find our exact values of 30 degrees or pi on 6 radians. So we have a right-angled triangle. We're interested in finding sine, cos and tan of 30 degrees. So our angle of reference here is 30 degrees, which means that the side length that's opposite that angle is the opposite length. That is 1, and the side length next to that angle is the adjacent side length of root 3, and obviously the longest side is always the hypotenuse, which has length 2. So now, as I said, it's simply SOHCAHTOA. So sine of theta we know is equal to opposite over hypotenuse, which means in this particular triangle, sine of 30 degrees is equal to 1 over 2. Similarly, cos of theta is adjacent over hypotenuse, so cos of 30 degrees or cos of pi on 6 radians is root 3 over 2. And tan is equal to opposite over adjacent, so in this particular triangle, tan of 30 degrees is equal to 1 over root 3. And we can repeat this time looking at 60 degrees or pi on 3 as the angle of reference, and so that's going to change around what becomes the opposite and what is the adjacent side. So now the opposite side is root 3 and the adjacent side is 1, the hypotenuse remains 2, and we can again use our Year 9 trigonometry to establish that sine of 60 degrees is root 3 on 2, cos of 60 degrees is 1 on 2, and tan of 60 degrees is root 3 on 1, which is just root 3. And lastly, our exact values for 45 degrees or pi on 4 radians. We use the second of the special triangles, and here we can see again that the opposite and adjacent sides will both be 1, and the hypotenuse length is root 2. And so that means that sine of 45 degrees or sine of pi on 4 is 1 on root 2. Cos of 45 degrees or cos of pi on 4 is also 1 on root 2, and tan of 45 degrees is 1 over 1, so just 1. And we can summarise all those calculations in the table. Now you need to find some way to remember these values. So whether you know those two triangles and you can generate the values each time, which is what I do, or you might decide that you're going to sit down and learn this table just by rote. I think that can be slightly risky because it's very easy just to make an error in this table and not have thought about whether or not you're correct. But that's, some people have great memory and can do it in that way. The other thing you might know, if you're going to learn this table by rote, there are some quite nice patterns that happen in the values. So if we look at the values for sine of theta, and obviously we need to be clear that our values for theta are in numeric order from the smallest angle to the largest angle, we actually get these quite nice patterns. So if we think about 0, we could write 0 as square root of 0 over 2. Now that seems completely pointless on its own, but as you look down the column you'll see why that makes sense, because sine of 0 degrees is square root of 0 on 2, sine of 30 degrees is square root of 1 on 2, sine of 45 degrees is square root of 2 on 2, sine of 60 degrees is square root of 3 on 2, and sine of 90 degrees is the square root of 4 on 2. So that makes it easy to recall them. You just will then need to simplify them, particularly obviously the root 0, root 1 and root 4 need simplifying. It's quite acceptable to state sine of 45 degrees or sine of pi on 4 as root 2 on 2. Root 2 on 2 and 1 on root 2 are exactly the same value. One just has a rational denominator. And obviously we should already have noted that the values for sine and cos switch around, and that's to do with the fact that they come out of that same special triangle. We just switch what's the opposite side and what's the adjacent side. And so the values in the cos column can also be established using the same pattern in reverse. I'll talk about how we can establish, once we know the sine and cos values, we can also then work out the tan values in just a moment. There's a relationship between sine, cos and tan. So the other way you might choose to remember them is to picture this first quadrant of the unit circle and picture these sine and cos values actually as coordinates. And so you could draw this diagram or just be able to recall this diagram in your mind. Again, the diagram, because we're only looking at the x and y coordinates of a point on the unit circle, we're only getting the sine values and the cos values from the coordinates. But tan can be calculated once you know the sine and cos values, because tan theta is equal to sine theta over cos theta. And let's just have a little quick break here and have a look at why that's so. And to do that, we need to return to our definitions of sine, cosine and tangent from the unit circle. We see when we construct this diagram for the definitions of sine, cos and tan, we've actually created two similar triangles. So the smaller triangle within the unit circle, triangle OAP, is actually similar to the larger triangle OBQ, and that's because each of those two triangles has the same angles. They're each right-angled triangles, they each have that angle of theta, and hence the third angle will also be equal. So since they're similar, the side lengths of these two triangles are in the same ratio. That is that QB over OB is the same as PA over OA. And if we substitute our expressions for those lengths into this ratio statement, we see that tan theta over 1 is equal to sine theta over cos. Just note that that 1, the length OB, is obviously 1 because our circle is a unit circle. It has a radius of 1. And so we know then that tan theta is equal to sine theta over cos theta. So going back to our circle here, if, for example, we know that cos of pi on 4 is 1 on root 2 and sine of pi on 4 is 1 on root 2, then tan of pi on 4 is 1 on root 2 divided by 1 on root 2. So it's going to be a little bit of work to work that out, which again is why I think a straight memory of the table or this quadrant and then requiring calculation for tan is not as efficient as using the special triangles.